Well, hello everyone. Let's get started with today's lesson. We're going to be looking at lesson 14, the nuclear charge, in your study guides. So if you get those study guides out, let's get started with lesson 14, the nuclear charge. All right, here we go. All right, let's start off with a definition of what the nuclear charge is. Simply, it is the number of protons in the nucleus of an atom. Now, you're going to say, well, wait a minute. Doesn't that sound very similar to the atomic number? And the answer is, yep. The atomic number is also the number of protons in the nucleus. But the nuclear charge has a little bit more meaning that's related to Coulomb's law and the attractive nature between the nucleus, the protons in the nucleus, and the valence electrons in the outermost shell of an atom. So, as we know from Coulomb's law, if I increase the number of protons in the nucleus, it should increase the attraction between the negatively charged valence electrons and the positively charged nucleus. And so what we're thinking with nuclear charge is not just the number of protons, but the fact that we're thinking about the amount of positive charge in that nucleus. So if I have a nuclear charge of 1, that means I have 1 proton, versus a nuclear charge of 2, which is 2 protons. But which one has a more attractive nature between the nucleus and the valence electrons? Well, it'd be a nuclear charge of +2. So really, nuclear charge goes beyond just the number of protons. It's also related to how attractive the nucleus is to the valence electrons in that valence shell. Okay, so keep that in mind. Now, by the way, we use the letter Z to symbolize nuclear charge, all right? And again, we can think of this, the higher the nuclear charge, and as it increases, it's going to increase the nucleus electron attractions and then results in a lower energy of the attracted electrons, okay? And we've talked about this, that electrons really structure themselves within the atom in order to lower their energy state. The lower the energy state for an electron, the more stable that electron is, but the more stable the overall atom is. And so as you increase the nuclear charge and increase then the electrostatic force between the nucleus and the electrons, especially the valence electrons, then the energy reduces and the electrons become more stable, okay? Important to remember and understand, right? All right, so this diagram represents some atom. We don't know what the nuclear charge is, but let us kind of say that because we have 1 proton or 1 electron here and another electron here, and this is an electron, we're just putting negative charges here. So we have essentially 5 electrons. So probably the nuclear charge, if this is a neutral atom, is +5, okay? Which really means that we have 5 protons in the nucleus. And all 5 of these protons are attracted to all of these electrons in the atom. But we're really focusing on these 5 protons attracting to these outer valence electrons. And that's what's really the most important part of our discussion, is the attraction, the electrostatic attraction between the nucleus of the atom and the valence electrons, okay? Now, if I add another proton to this nucleus to create a nuclear charge or increase that nuclear charge to +6, all right, what's going to happen to the attraction of the valence electrons to the nucleus? Well, according to Coulomb's law, if I add more positive charge to the nucleus, that nuclear charge goes up, so does the attraction on the valence electrons in that outer shell. Okay, so that's important to make a clear understanding of, right? All right, now there are other attractions and repulsions that are going on simultaneously in the atom. Okay, so in this drawing, not only do we have, and let's go back to our positive 5 nuclear charge, 5 protons in the nucleus. Okay, now this electron and this electron are the valence electrons. You know that, and the valence electrons are attracted to the nucleus. But we also have these other electrons that are the core electrons, right? And the core electrons, there are any electron that is not found in the valence shell, as a reminder. And so what's happening here is, yes, the core electrons are attracted to the nucleus, absolutely. But we also have some repulsion going on. Because the electrons have similar charge, the core electrons are going to repel the outer or valence electrons, okay? So the repulsion forces that are occurring here have a big, giant effect on the overall attraction between the nucleus and the valence shell, all right? Now, these repulsion forces result in what we call the shielding effect, okay? The shielding effect. And that is essentially, by definition, in multi-electron atoms, each electron feels not only the attraction to the nucleus, but also the repulsion from other electrons, okay, which we just described. We've got attractions and repulsions on these valence electrons here, okay? Now, repulsions counteract the nuclear attraction somewhat, making it easier for the electrons in the valence shells to be removed. So what we're saying is that these electrons in the core act as kind of a shield, and they shield the valence electrons from the nucleus. Okay, you can kind of think of maybe a force field, sort of. It's not really a force field, but you kind of visualize that maybe it's this force field that surrounds the nucleus. And therefore, the attraction between the nucleus and the valence electrons out here is not as great of an attraction as we would expect, because the shield, those other inner or core electrons, are shielding the nucleus from fully attracting the valence shell. And that is called the shielding effect, okay? Now, if there were no core electrons at all, got rid of all the core electrons, then there would be no shielding effect. And the nucleus would have a full-on electrical attraction on those valence electrons. But as soon as we add core electrons, the shielding effect takes place, and therefore the nucleus cannot fully attract the valence electrons as much as it would without the core electrons, okay? And by the way, the shielding effect does increase when you add more core electrons, and that's important to remember. The more core electrons, the greater the shielding effect occurs, and the bigger impact it will have on the electrostatic force between the nucleus and the valence electrons, okay? So keep all this shielding in mind as we go through the next several lessons on these nuclear attractions to the valence electrons. All right, so as a result, we get a new definition of nuclear charge, and that is called the effective nuclear charge. The effective nuclear charge is the real nuclear nuclear to valence electron attraction, with counting in the shielding effect, okay? So if you don't have that shielding effect, you just have the nuclear charge. But if you have those core electrons shielding the nucleus, then you do have the effective nuclear charge takes hold, okay? So again, you can think of the effective nuclear charge is the real attraction between the nucleus and the valence electrons, taking in account of the shielding effect, okay? So we will often use the effective nuclear charge in addition to saying nuclear charge. All right, so let's take a look at the periodic table real quick and see what's going on here. All right, as we go across, let's take the third period, for instance, okay? As we look at period 3, okay, we know that going across the period from left to right, that essentially we can count on the number of protons increasing in the nucleus, right? So going from 11 to 12 and so forth across. So if the number of protons are increasing, right, along a period, then what's happening to the effective nuclear charge? Well, it also must increase, okay? So by increasing the number of protons going from left to right, the effective nuclear charge is also increasing. So you might want to indicate that. Going across increases the effective nuclear charge because we're adding more protons to the nucleus. Now, the question is, does the shielding effect matter much as we move across the periodic table? And the answer is no, okay? When we're adding a proton to the nucleus, we're also adding an additional electron, right? But where are we adding the additional electron? Well, we're adding it to the valence shell and not to a core shell. So therefore, when I take sodium and I add 1 proton from sodium to magnesium, magnesium also gains an additional electron, but it goes into the valence shell and not a core shell. So therefore, the shielding effect doesn't really impact the nuclear charge or the attraction between the nucleus and the valence electrons as we're moving left to right across the periodic table. That's something you should make note of, okay? Write that down, review this statement because that's important, all right? So that's essentially going across the periodic table. But what about going down a group? So let's look at group 1, for instance, okay? If I go down group 1, you will notice that the nucleus is going to gain more protons, right? If I go from lithium, that has 3 protons, to sodium that has 11 protons, that's a big jump in the number of protons in the nucleus, and that continues to go down, right? So we would assume that by adding these more protons, that the effective nuclear charge is increasing as we're going down. And that is true, it does. But we also have to account for one other problem, and that is we're also adding more electrons to those atoms as well. Well, where are we adding those additional electrons? Well, we're adding them to the core level, because as we're going down, remember that we're adding actually 1 more electron shell. We have 1 electron shell, and then we add a 2nd electron shell, then we have 3 electron shells and 4. So every time we're moving down a group, we're adding an additional electron shell. You know that, okay? Well, that means we're also adding more core electrons because the valence shell is going out, right? So if I'm adding more core electrons, that means the shielding effect is also increasing. And so anytime I'm adding more electrons to the core, as I mentioned, I will increase the shielding effect. Therefore, the attraction between the nucleus and the valence shell goes down. So even though I'm increasing the number of protons, I'm also increasing the shielding effect. And that's going to offset the increase in nuclear charge. Okay, hopefully that kind of makes sense. Let me kind of repeat that again. Yes, the nuclear charge is increasing as we're going down because we're adding more protons. But at the same time, the shielding effect is also increasing because we're adding more electrons to the core. So that's going to offset both of those ideas. All right, and that's gonna make a big impact on the overall attraction between the nucleus and the valence shell. Okay, in reality, as we go down a group, using group 1 as an example, the attraction, write this down, the attraction between the nucleus and the valence shell decreases, okay? Remember, as we're going down the periodic table in a group, we're adding more electron shells, okay? That's making those electrons further and further away from the nucleus. Specifically, the valence electrons are getting further away from the nucleus. And because those valence electrons are getting further away from the nucleus, the protons in the nucleus has a less of an attraction on the valence shell. Okay, so let's summarize this really quick, and then we'll start finishing things up. All right, let me clear everything here. All right, as we go across the periodic table, left to right, the effective, E for effective, nuclear charge is going to increase, okay? That means, as a result, and write this down, that means as a result, the attraction between the nucleus and the valence electrons increases. I'm going to repeat that one more time, and please write that down. As we're moving across the periodic table left to right, the effective nuclear charge is increasing because we're adding more protons. That's the reason why, that's the why. Therefore, as a result, the attraction, the electrostatic attraction between the nucleus and the valence electrons increase. Okay? Really important. Okay, I can't stress how important that idea is. Okay? Now, let's look at going down. Going down, the attraction between the nucleus and the valence shell is not really being determined by the increase in protons, because by increasing the protons, I'm also increasing the shielding effect, and that cancels out. So the real factor here that is determining the attraction between the nucleus, the protons, and the valence shell is the distance. Coulomb's law, the distance, okay? The distance is increasing as we're going down a group. And the distance is because we're adding one more shell. And as we're adding more shells, the valence electron and the nucleus is getting further away. So what happens is that we can say the attraction goes up, okay? The nuclear attraction is actually going up or increasing as we go up, all right? So lithium has a greater attraction for the valence electrons than sodium does. Sodium has a greater attraction for the valence electrons than potassium, and that is just because of the distance. So going across is based on the number of protons in the nucleus or the increase in nuclear charge. going down the periodic table, it's really based on the distance that an electron, a valence electron is from the nucleus of an atom. Okay, I hope I've nailed that and made that clear enough because that is really super important for you to understand. Okay. All right, so finally, let's finish this off. All right, so I have a nucleus here with 6 protons, and here's all of the electrons. So let me ask you this, between electron 1 and electron 2, which one is going to have the greatest attraction to this nucleus? Okay, well, I would say electron 2 would have the greater attraction, and that is because electron 2 is closer to the nucleus than electron 1. And again, that goes along with Coulomb's law, right? As the distance between the electron and the protons increase, the electrostatic attraction diminishes and goes down, okay? So electron 2 is more attracted to the nucleus than electron 1. Okay, now let's look at the second atom. We have 8 protons. So again, which electron is more attracted, electron 4 or electron 5? Hopefully you said electron 5. Again, same idea that electron 5 is closer to the nucleus than electron 4. Now, let me ask you this then. Comparing these two atoms between electron 2 and electron 5, which one of those two electrons is more attracted to its own nucleus? Okay, think about that. Which one of these electrons, 2 or 5, is more attracted to its nucleus? If you said electron 5, you would be correct. And that is because electron 5 has a nuclear charge that is facing with 8 protons, so a nuclear charge of 8. So 8 protons has a greater attraction for this electron than the 6 protons for number 2. Okay, and that's also applied to Coulomb's law. As the nuclear charge increases, so does the attraction between the electrons and the protons. Okay, all right, so keep that in mind. These principles are really important, and they will be applied to many situations when it comes to understanding the properties of an element and those attractions between the nucleus and the valence electrons. Okay, so study this lesson. If you need to go back and review this video, please do so. But that's it for this particular lesson. So we'll see you next time then, okay?